So we've thought a lot about conceptually how to think about acids and bases, their relative strengths, and we've done a little bit of allusion to thinking about that in relationship to equilibrium and the equilibrium constant. And what we're really moving towards is migrating all of those together so that we can think about pH, equilibrium, and how to compute those sorts of things in solutions. And we're going to start with the simplest case of those solutions, which are strong acids and bases. And so I mentioned in a previous video an example of strong acids would be things like nitric, HCl, hydrochloric acid, or perchloric, HClO4. And these three that I'm listing here are specifically examples of monoprotic strong acids. And the mono comes from one, meaning they each have just a single proton or hydrogen ion to donate. Because of course we have things like H2SO4, which is still a strong acid, but we consider that a diprotic strong acid. So we'll talk about those later. So in an example of a strong monoprotic acid like nitric acid in water, when we say it's strong, what did we already indicate about where that equilibrium would lie? And how can we use that to understand what it would produce? Well, of course, that's the acid, HNO3, that's much stronger than water. And so that's going to produce, in this case, the hydronium ion, H3O+, and the corresponding conjugate base, which is just the nitrate ion. And our understanding of this would be, well, if this is really strong, then we would expect this thing to lie very far to the right. And specifically, when we talk about strong acids, we're talking about things that dissociate 100%. If they dissociate 100%, then that means all of that nitric acid, HNO3, will get converted to the nitrate and corresponding H3O+. That's what strong means. In other words, strong acid means that you don't have any of the acid actually in solution. It totally dissociates. What you really have is H3O+, which should make some sense because this is the actual metric for acid strength, right? That is the negative log of that concentration that tells us what the pH is. And so it's really nothing to do with the acid itself. It's how much hydronium ion does it produce at equilibrium that tells us the actual strength here. So let's pretend that we have a solution of 0.025 molar HNO3 in water. That's a strong acid. Conceptually, no, that's 100%. It's going to totally dissociate. So what's the pH of this system? Well, we just said the pH is the negative log of that hydronium ion concentration. So how can we go from the concentration of this thing to the concentration of this thing, knowing that it's going to dissociate 100%? Sort of the other way to phrase that is that if we have 100% of the nitric acid dissociating, then that just simply means, at least stoichiometrically here, that whatever we started with, whatever that initial concentration of HNO3 was, and I'll just write that with a naught down here, that's got to be equal to H3O+, because every one molecule of HNO3 produces one of these, and it 100% dissociates. And we also know that the initial concentration of that nitric acid was 0.025. So we could use 0.025 as the concentration of hydronium ion, again, assuming our knowledge that this is a strong acid and it will dissociate 100%. So if the goal was to compute pH here, then I would just do negative log of 0.025, because that is the implied concentration of H3O+. There are two sig figs in the 0.025 number, which means I get to conserve 2 past the decimal in my logged version, the pH version, which gives me a value for pH of 1.60. We know that any value less than 7 is acidic. This makes a lot of sense. This is a pretty dilute concentration of acid, but it still yields a very acidic pH. So what about strong bases? Well, strong bases typically are of the group 1A metals, the alkali metals, when they are combined with the hydroxide, the OH. And so you have things like NaOH, which we call sodium hydroxide, or KOH, which is potassium hydroxide. But the same logic applies. It just means that you have 100% dissociation of that compound in water, thereby producing lots of hydroxide ion. Remember, if we have lots of hydroxide, then we have very low hydronium ion concentration, which means that we are at a pH above 7. That's a basic solution. So what about the example of 0.1 molar sodium hydroxide in water? How could we figure out the pH knowing that it's a strong base and it completely dissociates 100%? Well, we can draw a very similar conclusion that we did with the strong acid. So because it's 100% dissociation, NaOH is just going to break up into its sodium ion and hydroxide ion. So there's sodium ion plus hydroxide ion, and if that's 100% dissociation, then we can say, well, whatever the initial concentration of sodium hydroxide is at equilibrium, we're just going to have all of that now fully dissociated in the form of hydroxide. So initial concentration NaOH is the same as equilibrium concentration. And we can use our trusty equilibrium expression for the dissociation of water. I just already rearranged it. Here I'm using H plus instead of H3O plus. Doesn't matter. I'm just doing that for shorthand. Remember, if that's foreign to you, take a quick look at the previous video, that quick note on different ways to write auto dissociation of water. But this has to be true. And we know now from this assertion that we can plug in 0.1 for the hydroxide ion concentration, solve for the proton concentration. That gives us a value of 1 times 10 to the minus 13. So that's very low concentration. And we are looking for the pH, so we can do negative log of that. And we get a value of 13.0. Remember, sig figs here, so let's see, that should actually be 13.00. Good check, because we have 2 sig figs in this number here, which means that we should have 2 pass the decimal here.